B part 6, exterior algebra. Now lecture 4, analogy between two forms and the cross product. You see, this analogy is in my viewpoint, you see, because I didn't see in the literature, okay, videos, books, okay, this analogy. So I think should be better for you to understand exactly the analogy between the cross product and the wedge, as you see here. So consider the Euclidean system belongs to R3. You see, these are orthogonal bases I, J, K. Now we know that I is a cross product between J and K. Likewise, K cross J is minus I. J is K cross I. I cross K is minus J. So K is I cross J. J cross I is minus K. You see from here, from the definition of cross product. Now, let's make analogy. You see, you can see here that I is equal J cross K. So this is I, you see I over here, I set J cross K. This is J, I set K cross I. And this is K here, I set I cross J. You see this analogy here, this is not analogy, that's what I should do it, it's clear. Now, you see also that I cross I is equal 0, J cross J is equal 0, and K cross K is equal 0. From the definition of cross product, from R3, you see, classical mechanics, electromagnetism. Now, let's make analogy. Okay, let's denote the symbol wedge is related to the cross symbol here. And then I just substitute, you see, J by dy, K by dz. So this corresponds, okay, for analogy that there's a unit vector here, I. You see? Likewise, this J here, J, you see, is, just look at here, K cross I. K is analogous to dz and I analogous to dx. So this I substitute this cross symbol here by the wedge. Likewise, dx wedge dy. You see here, I dx j dy. So this analogy, okay, let's use the property of the cross product. You see, I will transfer this property to this case to the exterior algebra. Then you see that dy wedge dx is minus dx wedge dy. You see the cross product, one is equal minus one. You see from here, you see clearly. So dz wedge dy is minus dy wedge dz. Likewise, dx wedge dz is minus dz wedge dx. So this is skew symmetric. You see, like this. You see, this is skew symmetric. Now, dx wedge dx will be 0. Why? Because I cross I will be 0. So dx wedge dz is minus dz, okay? This over here, I'm here. You see, dy cross dy is equal 0, dz cross d wedge dz is equal 0. So this is a wedge. The analogy between this one and analogy between this one, you see, is analogous. You just substitute y by this case, y by dx, I by dx. You see, dx wedge dx is equal 0. Since they are skew symmetric. Now, you see this analogy? Now, I will apply this the analogy just to solve an example, you see. So given the one form, omega y3z dx plus xy dy plus xz dz. Why this is one form? Because you see, the basis is dx, dy, and dz. Like here, the basis is I, j, and k. You see the analogy here. Now, I give this and obtain d omega, okay? Now, omega is a one form, so this f1 is function of x, y, and z. dx plus f2, which is a function of x, y, and z in general, and f3, dz, f3 is function of x, y, and z. This here is one form. It's one form. Why it's one form? Because this is expressed by the basis dx, dy, and dz. Okay? Now, for dx, dy, and dz, this is a constant, like ijk. You see ijk, okay? I assume that's a constant, you see, because this is Euclidean coordinates. This is analogous. So I just take the differential of omega, differential of f1 from here, differential, this case, for f2, and differential of f3. And I repeat the x, dy, and the z, because I'm assuming this is constants, analogous to ijk. Now, that's important here, so that to emphasize that f1, f2, and f3 are zero form, are functions. Okay, dfi, okay, is one form. Okay, this y is one form. You see dx, dy, and dz. Then I set df sub I. This is I is equal 1, 2, 3. I could repeat this 3 times for I is equal 1 or 2 or 3, but I think it's better that to write here. So this is 3 relation for I is equal 1 or I is equal 2 or I is equal 3, because this is a free index. See? Now, let's work on this. Let's give f1 y3z df1. You just apply the differential f1. This is partial f1 respect to x. There is no x here, so this will be 0. Plus 3y squared z dy plus y3z z. Likewise f2 xy. Okay, there is no z here, so df2 is y dx plus xy plus 0 dz. f3 is xz, there is no y here, that's why partial derivative of y is equal 0. So this is z dx plus x dz. Now, the term 1, def1, this is wedge dx. I repeat, you see here, df1, I just copy from here to here, you see? And this wedge dx. Attention, remain the order. You see, this is dy wedge dx. This is dz wedge dx. Okay? You must, this case remains the order. So from here, you see clearly that dy wedge dx is minus dx wedge dy. Analogous to cross product. Likewise, dz wedge dx is minus dx dz. Now, this term 2, I do the same. You see, this is a y dx plus xy. You see, I suggest for you to have a piece of paper and copy and compare. You see that's quite clear. So I substitute the f2 over here. This is wedge dy. You see? Now this will be y dx, you see? Attention now, dy, wedge dy is zero from here, okay? Because this is analogous to this one. You see this line here, you see? I'm using like this. So df2 wedge dy is equal y dx wedge dy, because y dy wedge dy will be 0. The same for df3 wedge dz. I copy df3 from here and set over here wedge dz. Again, dz wedge dz is 0 because the wedge is analogous to the cross product. So this is z dx plus, in this case, z dx wedge dz. This relation 1, 2, 3. Now I just summing 1, 2, and 3. This leads to this relation here. You see? That's quite easy for you to see. So this is a two form obtained via rules of exterior calculus. The operator d increase the order of the form. You see, you have a function df is one form, and I have, for instance, a d omega. You see, if omega is one form, d omega will be two form, and so on. As you see, this application in other examples. You see, you say clearly here, you just copy, okay, and check, just to understand what I did, okay?